Welcome, everybody. We're going to be working on Unit 9 this evening, talking about the elements of deep learning. Deep learning is based upon neural networks, which is a concept that goes back a little ways in time, and is really kind of one of the fundamental concepts, basically, of artificial intelligence when it comes down to it. I'm going to pull up the PowerPoint here in just a moment. And I'm going to go into slideshow mode. Flop my screens here. We will get rolling. All right. So last week we were looking at machine learning. We even got to the point where we were kind of looking at some of the primary algorithms and tools and and the theories behind like how some of those models work. This week we're going to focus on deep learning, which is kind of like a subset of machine learning, if you guys remember. So it's kind of like a deeper level of it. The primary topics that we're looking at, what is a neural network, the inspiration behind neural networks, and some common deep learning models and how they're applied in the real world. This is something that's being used now, and you'll see like some of the usages of it are pretty darn cool and exciting, real frankly. And there's some really cool links that we have here in the slideshow to explore. So I'm kind of eager to get to those. You know, we can't start the conversation without first going into what neural networks are. And neural networks were something that are built upon the concept that the human brain is a superior kind of processing mechanism. It's basically a computer in a way, right? And so when we start building computers or thinking about mimicking what the brain does, and to build artificial intelligence, for example, we can't help but think about the human brain as kind of a model for that, and that's really what this kind of pulls from. Now, notice that, by definition, it's a computational learning system that uses a network of functions inspired by the neurons of the human brain. The intent is to mimic that. They were first proposed in 1943 by Warren McCullough and Walter Pitts in the University of Chicago. So right in our back door, right? So like some important concepts being developed right here in our backyard, basically. You'll see these diagrams here when we talk about neural networks, where we have these input layers, output layers, and layers in between that are hidden. And then there's this whole matrix of pathways that you follow in order to go through the neural network. And that's kind of the mimicking of the pathways in the human brain. And just because we have a pathway that's possible doesn't necessarily mean we follow all of them. And you'll see that when we run some live models later. I talk about the history of it a little bit. So we look at 1943 as kind of this inception year. And that's when we first created our very first mathematical model of a neural network. So somebody, even though, mind you, there was no fully electronic computer system at that point. They have electromechanical systems. They were just about to build ENIAC, which is the first fully electronic one. And, we were decades and decades away from the technology that we have now, where basically we carry a supercomputer in our pocket in the form of a cell phone. And they were still thinking about the capability that computers would eventually bring. And they start with the math. And this is one of the things that you guys are, maybe either loving or cursing, is that most of this stuff is built on top of mathematics and mathematical concepts. But the fact that they were defining it mathematically back then is very impressive, that they were thinking about it on such a deep level. In 1949, this book came out called The Organization of Behavior, which was built on top of some of these concepts of the neural networks. And, kind of doing this comparison between the brain and how we could mimic that electronically. In 59, they came out with two neural network models, one called Adeline and Madeline. And then in 1962, they started adding adjustments to those models in the form of weighting. And this is where we start to add some of those hidden layers in the model. And then by 1982, they had bidirectional lines for neurons. So in other words, the way that you could traverse the model, and you'll see these models represented with all these like lines moving around. And when we do the live example in the browser in a little bit, you'll see some of that too. But the fact that, you know, that the neurons can kind of travel almost in any direction at the same time. Then by 1986, they had multiple layers of neural networks that they were actually working with electronically. And so this work's been going on for a while. It's not brand new. That's a huge aspect of it. You'll notice on the right sidebar here, they, you know, like if we had like a 4-hour class, we might actually do this activity. We would have you maybe do a little like on the fly research, right? But you could very much take all of this information, right? Because you know, I'm encouraging you guys to experiment with Gen AI engines, drop it into a Gen AI engine and ask it some of the questions that are here. Like, who are the people that really built these things? What did these things do? What are the significant events in the development of neural networks? Of course, there are a bunch of you know, things here that you can read up, you know, and so notice, you know, from the 40s to the 70s, from Stanford, and the 80s to the present. So these are both pretty good reads. I'm obviously not going to do that here, but you could take a look at those and augment your learning is what I would recommend. Let's move on. So what makes it a neural network? So once again, we go back to this diagram. So we have our inputs and our outputs. Then we have all the stuff that happens in between. And the inputs all map to every possible hidden perceptron. Those like circles, that's what we call them. And we think of them as nodes or perceptrons, and they are basically typically a feed forward structure. So in other words, the data flows through in a certain direction, and it's from the input to the output, as you might expect. Each layer can have anywhere from a few nodes to many, many nodes, or even hundreds or thousands of nodes, by the way. And each one of those nodes is called a perceptron, right? So it says here, basically a neural network is a combo of multiple perceptrons, each arranged in different layers, right? Once again, to try to mimic the structure of the human brain. So I don't know if you guys remember this diagram from the previous weeks, but this is where we have the types of inputs that we're dealing with. And I want you to look at like some of these mathematical expressions, especially on the input side. So often you will have something like a constant that you feed in. So like a hard-coded number, so a hard piece of data that you're throwing in. And then you will have a combination of different functions, basically. So in other words, we don't know what numbers are being fed in here, but basically these are mathematical functions where we feed in a value for X, hoping to get some sort of an output based upon it. And those can be all sorts of different types of formulas, either knowns or unknowns, using different types of mathematical equations, which could be linear equations or nonlinear equations, you know, such as, you know, sine and cosine, for example. Those values are often weighted. So in other words, we put a value to each type of input, and then they create what we call a weighted sum. Yeah, and that's kind of a calculus thing, right? So like we're combining all these different inputs together, different types of mathematical formulas, and to create like a conglomerated output, and then that comes out. And this is based on the individual perceptrons, by the way. So here's an actual link out to a free tool on the internet, and this is amazing. I'm going to bring it up on screen here, but basically what it allows us to do is play with a pre-configured neural network, and you get to choose how many nodes you want, how many layers you want. You can add to them. You can change a bunch of the different settings, and then click it to run, and you can watch it iterate. Like it basically does it over and over and over again, like how a real neural network does deep learning. So I'm going to go ahead and click through to this. So let's bring that up on screen. And you guys should do the same if you have the capability to kind of pay attention to the Zoom session and play with the tool at the same time. Now, what's fascinating about this, and I'm going to scroll down first, right? So, all right, so they do a little like talking here, like what is a neural network, right? It's a technique for building a computer program that learns from data. It is based very loosely on how we think the human brain works, right? And this is very assumptive, of course. First, a collection of software, neurons, are created and connected together, allowing them to send messages to each other. Next, the network is asked to solve a problem, which it attempts to do over and over, each time strengthening the connections that lead to success. So it figures out which pathways work, which pathways do not, and diminishing the pathways that don't, right? For a more detailed introduction, you could read, these things. The fascinating thing is, and Python people and data analytics people, this is open source and it is on GitHub, so you can actually get the source code that creates this if you wish. And they talk about what all the colors mean. It also tells you which libraries, and the TensorFlow library is the predominant one here, and that's one that we use in teaching AI and machine learning in particular quite often. Very important one. All right, so I'm going to go back to full zoom here. So I'm at 100% zoom, and you can see some of the things on my screen. And you'll notice that there's kind of like this input layer. This is the output. And then there's, at least at this point, two hidden layers. But I want you to notice that with all of these layers, certain ones are enabled, certain ones are not. So for example, right now I have two X values coming in. And you notice as I hover over them, it indicates that this is trying to do, in this case, the problem type we're working on is classification. We're trying to classify data. And in this case, we're trying to classify data into stuff on the left or stuff on the right. And then we can also classify it stuff at the top or stuff on the bottom. And then we have neurons, right? And these are weighted. Notice how it indicates what the weight amount is. And notice how these neurons change the slope of like the orange and the blue sections. And we're trying to cover like on a diagonal. So these are up and down. These are on diagonals with the orange flipped, right, and the blue flipped, right, whatever. And then we have these other neurons here. So like basically these X's feed each one of the neurons, and then each one of these neurons feeds the next level, and so on. The fun thing is I can add more X's, so you notice how we have an X1 and an X2, but we also have X squared for X1 and 2. We have X1 and 2 as a series. We can also do the sine of X and the sine of X2, right, which gives us nonlinear shapes. We can look at the ratio of training to test data. This is set for 50% right now. So the combination of what it does is it trains itself and it tests itself. Half is used for training, half is used for testing. We can also introduce noise or stuff that doesn't really fit the data set very nicely, right? So if I do that, notice how the data gets scrambled in the graphic over there, right? Like orange mixes with blue. And we can also change the batch size, and then you can reset it all, by the way. At any point, I can add more X's, I can add more neurons, I can add more layers, and then see what it does. And then I can also go up here and change the learning rate, what algorithm we're using, what regularization we're using, the rate of regularization, and then the problem type, which is basically either regression or classification. Right, so you guys remember some of that terminology, I hope. And don't worry, you don't have to internalize this all immediately. This is just a fun tool to play with. It gives you kind of an understanding of like how this stuff operates. So I'm just going to take the given model that they have up on the screen right now, and I'm going to hit the play button. And as you hit the play button, I want you to watch the graph up here and how the graphic changes. Like it found that all the blue dots basically fall into this shape here. I want you to notice that it keeps running. And as it keeps running, it's finding the orange pathway and the blue pathway that works most efficiently. And at first, and I'll stop this and restart it. When I first start it, I want you to notice it doesn't really know which ones to follow. And as it proceeds, it learns and follows only the ones that work. You'll see the lines kind of intensify in color as it goes. All right, so that's just a brief example. Let's give it a challenge though. Let's add a bunch of, heck, let's add all this stuff, right? And you know what? 4 neurons isn't enough. Let's add a few more. And you'll notice as I add more, it tries to add neurons that do different things. And you know what? I can add more neurons over here too. And heck, I could add another layer, let's just go with that. That's pretty good. That's a lot to do right now. I'm going to go ahead and just hit the run on this. And I want you to watch the network as it propagates itself. And watch how the lines reinforce. Right. Now, after a while, it figures out what it is and puts it into different shapes. This isn't like super exciting. The neat thing is it's in browser and you can play with a lot of the tools and kind of see it in action. And I think the other fascinating aspect of it is once you do get to learn what all these settings mean, you can start playing with it. Now here's one that I'm just switching over to regression. I'm going to add a little bit of noise into the model because not all data is really clean. And maybe the batch size should be a little bit larger. And I'll leave these layers in here and we'll run that and see what that does. But watch that graph really shift here. It's a lot different. And it's coming up with different type of output altogether. Now regression, of course, is a different type of equation than classification. Classification was trying to put all the blue stuff together and all the orange stuff together. So play with that. It's kind of fun. As you learn more about this stuff, this will be a more meaningful model, but this is part of what we do. And you notice how we have tools like this that we can use graphically to build our models. Now, of course, we're not in control of any of the equations here or anything like that. But if we have very specific mathematical models that we're working from, those are the equations that would feed in. We can also control the data that goes into it as well. So there's all these different layers to this technology. All right, back over to the PowerPoint here. Not there. There we go. So why neural networks isn't machine learning good enough, right? These are some of the reasons for this. So first of all, you can use data as the input with little or no feature engineering. So in other words, if I was feeding especially structured data into a machine learning model, I got to get that data. I have to structure it, right? And so this is, one of the reasons, right? So if I just have a raw data set, I don't have to worry about like what data I'm feeding in. It just automatically adapts. So you don't necessarily need to be an expert about that data. And it allows you to kind of do some interesting things. And what's fascinating about it is neural networks get better results as you input more data into the network. It also can, on its own, discover unknown patterns that maybe we don't see. Right? When you have a small data set, you might see the patterns. But human beings in general, when we look at numbers, if it's all numbers and equations, we don't see the mathematical patterns. A neural network would find them. And it works better than machine learning when the data set is huge, right? So that's why we use that. That's one of the predominant reasons. It works well on things that are otherwise pretty difficult, such as image classification, object detection, and natural language processing. So a combination of those things. And if you think about all of those, they're all pretty challenging. So here's some examples. The fact that it recognizes our speech. Now, this one always blows me away, the speech one in particular, because we've had, for example, really efficient dictation software since the late 80s, early 90s on really primitive computer systems. People were already doing this. And I don't know how many of you are in the habit of like searching with your voice or typing a document with your voice, if anybody does that. But speech recognition has been pretty good for a while. Pattern recognition too. So like seeing a pattern in numbers or a pattern in shapes or something like that. Natural language processing, of course, is where it can actually understand what we're saying, not just taking a word and converting it into text, right? So speech recognition is when I say hey whatever, and it types hey whatever. Natural language processing is it understands that hey whatever is kind of a snarky non thing, right? It understands what I'm saying. It just does, it not only converts it, it understands it. A recommendation system is another one of those things. So for example, if you're surfing Facebook and 5 minutes before you were talking with your friends about, pick a topic, national parks, and all of a sudden you got little ads on your feed in Facebook about national parks, that would be a recommendation system. Or if you're shopping on Amazon and you're looking up computer memory, and then the next time you log in, it's like shows you all these things for computer memory or other computer related things. Facial recognition, another big area of usage for this. All right, let's move on forward here. So there's a bunch of different models that we use for deep learning. And some of these things we've talked about already, and some of this stuff we haven't. Here's a list of the popular deep learning models. So the important takeaway here is there's more than one, right? We're not going to go through each one of these here tonight. We are going to talk about some of the more important ones. And if you look at this list here, there should be at least one that you recognize. The number 4, right? The GANs, remember that? We've talked about that one, because that one is one of the ones that's heavily in use right now. But there are many more than the ones that we're seeing here. These are just some of the more popular ones. Move on. All right, so we're going to look at the first one on the list, which is the convolutional neural networks. And what it tells us here is that there's multiple layers. They're usually used for image processing and object detection. And if you start like kind of breaking this down, they show you the input. So they start with an image, right? So this is for image processing or object detection, right? And it goes through the convolution plus ReLU step, the pooling, and then it goes back to the convolution, ReLU step, back to pooling, and it kind of repeats that cycle. So it's kind of like narrowing down as it's learning or teaching itself basically what it's looking at. They show an example here of, they're trying to look at an image of a vehicle versus an image of what looks like handwritten number or text. What's fascinating about this field too is there's a technology called OCR, optical character recognition. That's another one of these like artificial intelligence things that's actually been around a really long time. And OCR software, I forget when it was like first out there commercially, I think in the 70s even, people were doing it. It didn't really catch on really heavily, I think, until like the early to mid 90s. But I remember at the university where I was learning and then ultimately working, we were in this transitional phase where, for example, we would have students in our MBA program that would write their master's thesis, and they would type it with either a typewriter or a word processor, and they would hand it in on paper. And those thesis documents would get stored in our library. So like if you went to, the Cardinal Stritch University Library, you can look up the thesis of any master's student that studied there. They were published, in our library. At one point, they had a directive to take all of those thesis papers and convert them to electronic format. So they would put them on a scanner, and then they would run a piece of OCR software that would read each character one at a time and convert it into a letter and type it into a word processed document if it didn't originally come from an electronic format. That's pretty fascinating thought. And even back then, it was pretty accurate, right? So it had to be able to read typewriter print, basically, and then convert it into text for screen. On occasion, it would make a mistake. I don't know if you guys have ever used OCR software. You can do it with a PDF document, by the way. You can take a picture of words, put it into a PDF, and then OCR it inside Adobe Acrobat. But it's not always 100% accurate. Some stuff is a little off. Right? So this is one of those models that works that way. When they look at this, you notice how they go through the convolution step, they do pooling, the convolution step, pooling, and what happens is as they go through the network, the results get better as they go through the network because it learns what works and what doesn't until it feels like it's pretty certain, and then you get your output, which hopefully is correct, with the emphasis on hopefully. This is a really important step in building a bunch of other types of object detection software packages. Probably the one that most of us have at least tried is number 4 with Google. Like if you guys have ever done a Google image search, right? You take a picture of something with your phone and you're Googling the image. Well, where did that come from? It hasn't been around forever. That's actually a fairly new thing. It's only been around for 10, 15 years. And now it's like just on everybody's device. Fascinating. But it is using a CNN network to do that technology. So they have these basically different key layers, right? So the convolution layer is one, the pooling layer that follows, and sometimes those repeat as we saw. And then they get to that ReLU, once again, part of that repeating layer, and then ultimately to softmax, which is where in principle it has done the classification and figured it out. So what each one of these does here, it's convolution is basically a math operation that filters the content. So it applies a filter to the input. It finds what we call high level features. So in other words, it looks at that picture of a dog or a cat and recognizes the general shape of one of those, right? There can be a few layers of that in the thing. The way that it kind of does it from a mathematical standpoint is using this sort of a model. And I want you to notice what the approach is here. They have this matrix here on the left, which is, I'm going to get my little pointer tool on here, if you guys don't mind. A large matrix that's 5 across and 6 down, right? And rather than kind of try to treat all the data inside of here as one collection of little individual pieces of data, it takes blocks of data, in this case 4 pieces of information, then uses this little matrix, right? And these are the weights. So, and we call that set of weights is what we call a kernel, right? So the 1, 2, 0, and 1. So these are preset values that then get basically processed with these pieces of information. And after we process those 4 pieces against these 4 pieces, we come up with 1 piece of information instead of 4. So we're kind of taking all 4 of those pieces of data, and now we have 1 piece of data to represent all 4. And the reason we do that is to simplify the processing, basically, because the more data we have, the longer the processing takes, but we can find mathematical ways to kind of conglomerate the data on that's really what this convolution step is. So for example, right, if you're wondering how they got to the number 9, right, so they got to the number 9 by taking 1 times 1, 2 times 2, right, so like corresponding position, 0 times 3, and 1 times 4. Here's the equation that forms. So 1 times 1 is 1, 2 times 2 is 4, so that totals up to 5. 3 times 0 is 0, it's still 5, and that's 4. 5 plus 4 is 9, so that's how they got to that number. Right? So if you want to do another example, you could move to the next set of 4. Notice how they're overlapping. And then you run the algorithm again, and this time you come up with 17, and you keep doing that, and you end up with a smaller, more processable data set ultimately. So, if we had time, I would make you guys do this, and you guys don't want to do this, right? This is maybe something we would feed into an AI and let it do the work for us. But in principle, I think all of you guys could do that math if you were so inclined, right? And if I was cruel, I would make you do it. Right? But here's the result of it, right? This is where it takes the one layer and does the pooling. So this is the pooling aspect that we're working on. It reduces the size, right? Because the dimensions are reduced, it decreases the computing power needed to process it. And there's 2 types of pooling layers, max pooling, right? And average pooling. Max returns the maximum value of the portion covered by the kernel, and average returns the average value. And you can see that both could be useful. So when we start to look at like, how do we compute the average, right? So it's not that much different, but in this case, we take all 4 values, right? All 4 values would be expressed here. And how many are there? There's 4. So we divide by 4. So these numbers add up to 11, and then we divide by 4, so we end up with 3, right? So we're taking these values and we're pooling them together to come up with one value, and it's rounded to the nearest integer. And you can continue that process over a matrix of any size of data. Another interesting thing here is when they start to do this ReLU thing, so that stands for, by the way, rectified linear activation function. The way that this algorithm works is any value of x that's fed into the equation that's 0 or below, they just set it to 0. There's no return from that. We're just looking for positive values of x. And then once we have that, then it's whatever your math model is that it will follow. And in this case, they're trying to maximize it with this example. Once again, don't freak out to the mathematical expressions. It's just a way of explaining what we're seeing visually. That's the way I think of it. So then you get to the softmax standpoint, where it's basically taking a result of all the different pathways that it's going through the neural network. And then basically each one of those is a function of some sort. And it says that it's a function that turns the values of each class into a list of values that sum to 1. So the total of all the output values will total 1. So basically these are percentages. And what we try to figure out is, all right, here's the image that's put in. It goes through the CNN, the convolutional neural network. It does the pooling, and it goes through multiple layers of it, might do it over and over again. And then basically these get ranked. And you'll notice that if a value is negative, so it's figuring out pretty quickly, it's not a horse. For sure, it's not a horse, right? And that's why we have a negative number here. Horse isn't hitting. It's like, that's off the table. That's not a horse. But most likely it's a dog, but every once in a while it is a cat, because cats kind of have the same shape head and, nose, ears, mouth, etc. And the end result is that it does this classification, and whichever one has the highest score is therefore determined to be the correct answer. So it runs it through the network and comes up with an answer by going through all of this. So anything that's got like a 0 value, I mean, you can cross that off. It's definitely not a horse. I don't know, maybe a really weird cat. but really it's a dot. That's kind of the point of it. Now the other one that we have talked about before are these GANs, right? And generative adversarial networks. And this is a really interesting technology. And we talked about it before, and it probably was like in one ear, out the other. I didn't really latch onto it. I'm hoping you get a little bit more clarity on it right now. Um, Now, read that first bullet. It's a generative deep learning algorithm that can create new data that resembles the training data. So, in other words, you feed it real information, and then it creates its own artificial information based upon the training data. So, for example, they're using images as the example here. So they can take a painting by Monet and have it generate a photograph that looks like the Monet painting. It's the same layout. There's clouds in the sky and a hill and a river and some buildings in the background, right? Or the horses, like this one is zebras, but let's just take the stripes away and now we have horses, right? I mean, because they're kind of the same sort of looking animal where you have like summer and winter or winter and summer, et cetera, et cetera. And this is kind of interesting. So this guy named Ian Goodfellow working at Google, and apparently they have a division called Google Brain, first introduced this in 2014. So this is technology that's only 11 years old, right? So this is really cutting edge stuff. So like, obviously a very brilliant person there. Now, the way that this technology works is there's kind of these two key components of it. One is the generator, and the other one is the discriminator. So the generator, as you can see, it says it learns to generate fake data. So whether it's an image or whatever, and they're using images as the example. So it generates, okay, so you have a real example to work with. It goes into the discriminator and it figures out, is that real or not? And then it also generates a fake version based on the real ones. And the discriminator's job then becomes to try to figure out, is that real or is it fake? So a GAN basically does that constantly. And what it does is, as it's going through the process, it learns how to create a fake that cannot be detected as a fake. I want you to think about that for a little bit, right? So it teaches itself how to create fake data that looks scaringly real, right? And they're kind of, and why do we call it an adversarial network? Is because it's kind of fighting itself. So we have one model that's using real data, and the other one that's generating fake data. And then the discriminator looks at it and goes, is that fake or is it real? Ah, that's fake. Well, if we tweaked it a little bit, it might look real, and it keeps tweaking it, and it finds the pathway that makes it look as real as possible. That's really kind of interesting. So, all right. So I guess I probably said most of this already, but let's see how it works. Data will be input into the generator to create fake data. Real data and fake data from the generator will be input into the discriminator. The discriminator will determine if it's real or fake, right? The predicted output from the discriminator and the actual output, the real data from the generator, are compared and fed back into the system. And it will repeat indefinitely, right? The objective of the generator is to create fake data that cannot be detected by the discriminator. The objective of the discriminator is to detect all fake data from the generator. So you kind of see like the challenge here. So by having it basically fight itself, it learns to improve to the point where the fake data cannot be distinguished from the real information. And that's really cool. So here's an example, and I am going to play this video here. Let's just run the video, and you guys can read the text as we're kind of going through it. I'll turn on the closed captioning here if it's available. And it's not available. Okay, let's. Not available because there's no audio. But I'm just going to run that one more time. So which is the real one and which is the fake? And it guesses. Well, it tells you in the title of the video, right? So they started with the video of the horse. They superimposed the stripes on top of the horse to make it look like a zebra, to the point where if you only saw one side of the screen or the other, which one would you think is the real one? Well, I would still, most people around here don't have. Oh, there you go. So who said that? Joe, right? Right. The zebra tail has stripes. That's probably not appropriate, right? If you ever look at a real zebra, that's a good catch, Joe. Right? That's how we can tell it's fake. So if you can tell it's fake, the discriminator cannot. But you have to admit, how long are you even staring at it close enough to even notice the stripes in the tail? Kathleen?
Just a quick question. What is the applicable point of this fake and actual of this particular model?
The point is to have the generated data look as real as possible, which is useful for other purposes, right? So, like, okay, creating a fake zebra, maybe not so useful. But if you were creating a model that needed to process faces, for example, for facial recognition, and you're training that model, it might be helpful to have some generated faces instead of going out into the world and getting a whole bunch of people to agree to have their photographs taken, so that you can see if they're real or not. That's kind of the rationale behind it. Seems kind of silly, um, but the synthetic data is really important in helping to train models, because often the real data costs money or is difficult to gather.
Okay, thank you.
You're welcome. Yeah, Jared's pointing out that zebras don't have tails like that. That's true. So, and actually, it's Kathleen, the answer to your question is actually on the screen right now. So, the first bullet says generate examples for image data sets for picture collections in various fields, including medical imaging, satellite images. GANs can provide fresh instances of images. In addition, researchers can enhance current data sets and the functionality of machine learning models by creating synthetic data. Generate realistic photographs may produce lifelike images of a variety of objects and settings, such as natural landscapes, domestic animals, and building. Or, for example, if you tell an AI to create an animal, I can probably find an image of one, and then instead of putting it in its native habitat as a background, you can create a synthetic background, that type of thing. Yeah. All right. There's another little video here, but let's some more examples. GANs are sometimes used to create cartoon characters or characters in films, and this is something I see in a lot of movies these days. Like you watch, for example, some people are, there's a close up of a couple of characters, and all of a sudden they're walking down city streets, and there's all these people and buildings. And do you know how much of that these days is generated synthetically? A lot of it, right? And the whole point is nobody's looking close enough to tell that they're fake characters, because it goes by so quickly, that type of thing. Or this one says turning photos into emojis. Oh, that's kind of an interesting usage. Here, let's play this quick video here and take a look. Right, so that's super, super fast. Now, what is the differentiation that's happening? What is that divider line doing as we're watching it? There's no words here. One is the real and one is the fake, right? I think the grayer one is the real image. And then when they pull the slider over, it's generating artificial data. And why would you do that? Why on earth would you do that? Well, if you're in the motion picture industry, whenever you put like a human being on film, you got to get their permission. If you capture them and then generate an artificial version of them, or like even the license plate on a car, that's acceptable because you're not really using the real person or the real license plate, right? But it's almost identical. Yeah, that's kind of one of the reasons for it. All right, moving on. Here's kind of some interesting things here too. GANs can also be used to take an image of somebody that exists, and these are like, you know, we don't really have a lot of motion picture footage of Albert Einstein, and we certainly have none of the Lady in the Mona Lisa painting. But notice how they took the image and they mapped it to who knows what, and they're generating basically what that person might look like in real life, right? These are all generated. These are not obviously the real Mona Lisa lady, you know, whatever the name is. But man, that's pretty creepy, right? To see those faces move like that. There's an app here that they're recommending that you tried. Has anybody ever tried this app? Like called the Face app? All right. This is really creepy. I have tried this in the past. This is only a mobile thing, so I can't demonstrate it on screen really. But what it does is it takes your face and creates a copy of it. All right, you guys feel where I'm going with this? So if you can create a synthetic you, then I can take my synthetic me and put it in different types of situations visually that I never was part of. Kind of an interesting thought, right? And I've seen people do this. I think it's super creepy. I'm not all about like, you know, creating a duplicate of myself, that's for sure. But some people might feel a little bit more comfortable with it. But this is a thing that some people are doing. And this video I'm about to play here is an example of a deep fake where somebody created a synthetic version of Tom Cruise and mapped it on top of somebody else. So it looks like Tom Cruise is the one in this video, but it's not. This is an artificial Tom Cruise. So let's just watch this really quick.
What's up, TikTok? Got a little tip for you. Call it a tip talk. If you don't have earbuds, okay, it's hard. It's hard to talk on the phone. It just keeps on falling out. So go old school, analog. Just get it involved. You got to plug it in. It's not wireless, but it's the better way. You know, I do all my own stunts, obviously. I also do my own music. I've got a sweet spot for a couple of artists, and people are surprised that I'm a big Dave Matthews guy.
Okay. Yeah, this is really weird stuff. But yeah, that's not really Tom Cruise. That is Tom Cruise's face mapped to somebody else's body. Right. And they're calling this a deep fake, right? So this is not a new thing, and I'm sure you guys have seen other videos like this. But I want you to think about the possibilities here. People are actually creating TV shows and movies with this technology now, and some of it is really astounding, especially when you get really high-powered computers behind it. So, for example, you can watch. I'm trying to think of like one series we were watching the This Is Us series. If you guys ever seen that one, right? It's an interesting series, but they would often show the characters when they were young and when they're old, and some of it is like, okay, yeah, it's makeup, but some of it isn't. Some of it is like, wait a second, you're already this age. How did they show you being like 15? You know? And the answer is with technology. So they would deep fake themselves, and they would have an AI create a younger version of themselves. They'd map that younger version onto the body. The regular actor just does the scene, but the AI is altering the appearance to be a 15-year-old. And it's like, oh my God, right? All right. But what about the questions here? Are there ethical issues with this? How do you think Tom Cruise feels about this? It looks like there's a whole series of videos of him doing this deepfake stuff. That's pretty weird, right? And oh my God, you could make it look like somebody committed a crime that they didn't commit, or somebody doing something wonderful that they never did. How do we tell the difference? These are some very, very deep questions, you guys. I don't know if you're feeling that. We'll move on. I think we're at the point where we want to take a break. Let's pause and do a 5-minute break, folks. All right, folks, we're going to kick back in. Hopefully you're all back. Any questions or comments before I roll forward? Laura?
I just wanted to add about the feature that you just mentioned. I know there's a movie called The Curious Case of Benjamin Button, and they did that with Brad Pitt because I was like, how can he look so young? Like now I'm understanding the
Yeah. Now, and Hollywood studios have like super high powered CGI, and prior to this technology being around, like CGI has been around for a while, right? So they could create like, I think of like the movie Avatar, but the way they would do Avatar is they would put like all these sensors on somebody's body and record that, and then they would map the digital features to it. Now that the AI engines can do that without that mapping, that's crazy. Or they can provide a photograph of the person when they were young and map that young face. Yeah, it's a trip, right? And if you start really looking at a lot of movies and TV shows that do it, there's a lot of that going on, and it's impressive actually. And there's kind of this conversation I was having with my son about this stuff, that, and I forget if I read this somewhere or whatever, but basically that how the younger generations are better attuned to spotting the fakes than the older people are, which I think is really kind of an interesting thing. All right, I'm going to go ahead and roll forward if there's no more questions. Here we go, folks. Well, apparently, once again, so I had this problem last time. The recording is still running. So I swear I paused it. So yeah, that's really weird. All right, so I got a lot of editing of videos to do tomorrow morning. We'll see how that goes. Either that or Zoom is automatically kicking back into record mode, which I'm uncomfortable with. By the way, I like to be in control of the stop start. So we'll see how that goes. All right, video editing forthcoming, apparently. All right, folks, let's move on to the next slide here. I'm going to pull up my annotation tools too. I like to get that little spotlight tool. I think is pretty helpful in some cases. All right, so now they start talking about the different types of generative AI, and they talk about how Gen AI engines are using these various technologies. So like in the last few slides, we were focusing on the generative adversarial networks, right? It takes real data, it creates a fake, it keeps trying to figure out if it's fake or not, and then improves the fake until hopefully it gets to the point where it doesn't detect it anymore. So that's the one approach, right? So, and really what we're doing is we have two networks working against each other, one detecting and one generating, right? The one using real data and the one generating false data. Another approach are the variational auto encoders. We talked about these very briefly also. And notice the way that this works, right? And it does produce fresh information, but it learns the distribution of data and then samples from it. So it kind of grabs random sample points in the data and recreates them. There's a couple of other approaches, though, really more than a couple of others, but these are some of the other ones. The recurrent neural networks, these are really good at handling data that's already ordered or in sequence, and they use the example of like music or text. So for example, like if you ask an AI to generate a story, let's say a comedy or something, it uses other examples of that, to like set up like the process of, what the narrative might be, because that's a sequential thing. Or if you're asking AI to generate a piece of music, music has patterns that it follows too, including repetition and like a refrain and a chorus and a verse and a bridge and things like that. There's also the autoencoder. So it's basically trained, if you notice the first sentence there, to learn a compressed representation of the data, and then it compresses the data first and decompresses it. So for example, whenever we transmit even video over the internet right now, it is going through a compression decompression process to travel over the internet, and it happens really quickly. Autoencoders can be applied to a lot of different things so that it appears that you're not losing any of the information. And then when it like is decompressing it brings back the lost information. This is kind of an interesting thought. It's kind of like a zip file is the same way, right? How does a zip file get so small? It's removing some of the information. How does it come back to what it was? Well, there's algorithms for doing it, right? The uses for that are for denoising or picture compression applications. Then we also have the deep belief networks. These are ones that are very, very data rich, by the way, but it simulates super complex, and it says high dimensional data. So in other words, very complicated data sets that are sometimes beyond 2 dimensions in their structure, right? When we think of like, for example, what do we mean by dimensional data? When we look at a table like in Excel, Excel is rows and columns, that's 2 dimensions. When we start to add additional tabs to our spreadsheet, that has a 3rd dimension, you know, et cetera. So this one, it takes a little bit more data crunching and stuff for sure. So they have this little activity here, and you guys can either pull this up on your phones if you want to use the QR code. Once again, I'm not on a phone here, nor do I have an emulator loaded up. You know, one of these days I should get smart, and I should run this class on my Mac, because the Mac has a built-in emulator of iPhone, right, that I can run inside the operating system and simulate some of this stuff. You can also go to this thing here if you wish, and of course it opens up on my other screen, so I'm going to pull that over. Give me a moment here. And basically this is a GAN-based image manipulating software that's browser-based. And I want you to notice that they have like a photograph that's loaded up on the screen, right? And you'll notice that there's these key elements of the photograph: trees, grass, a door, the sky, the cloud, the brick, the dome, whatever. And if I wanted, right, I can, for example, if I want to draw a tree, well, and it's set for tree right now, I can go on the screen here and try to draw a little bit. Notice I just created a tree, right? That wasn't there before. And it kind of looks like it's pretty real. Or for example, if I wanted to add a dome, I might come in here and do this, right? Maybe the dome needs to be a little bit taller or bigger. I'm kind of painting it in. And so it's generating, I want you to notice what it's generating this dynamically. It's been trained to do this, so you can use different images. You know, if I want to, I don't know, add some sky up here because there's too many clouds, I can kind of keep drawing in the sky until the clouds go away. Right? Pretty slick, right? And I want you guys to keep in mind, I'm just doing this in my web browser. Laura, go ahead and unmute and ask.
I actually tried the QR code and it's saying that it is expired.
Oh, okay.
And then I also tried the website and it says this connection is not private. It may be impersonating to steal personal and financial information.
Now, it works for me. You'll notice it'll come up as not secure. The reason it's not secure is because this is a university that sponsors this, right?
Okay.
So it is safe to go to. If you
Okay.
don't trust going to it, don't do it. But this is just an example of what you can do with this technology. And you notice, like, I don't have any expertise at this, but I'm like drawing in sky. Here, I'll make the whole image of sky, right? So I'm like kind of deleting the building as I go along. But, and then I can, you know, add stuff to it, whatever, you know. The point is that the technology is there, and it's in many cases for the taking. So that's kind of a fun one to play with. It is pretty basic. They do a little demo of it right here. This is kind of what it does. And it's kind of just fun to watch the graphics. So they're taking elements that are in the photograph and using it to recreate elements or remove elements in the photograph. Right. For any of you that might be subscribers to the Adobe Creative Cloud, that's been adding these types of features to products like Photoshop, where I can like take an object in a photograph, remove it, or take the subject of the photograph and create a different background. And AI does it. And in the past, you'd have to like do all this like fancy graphical work to make it happen. And now it's just become super easy to work with some of these tools. This is an experimental model from a school, but if you want to explore a really powerful application, Adobe Firefly is their AI tool. It's not free, by the way, but it is mind-bogglingly powerful, right? It is amazing, right? So if you guys can afford to try it, try it. All right, so here's another kind of usage for generative AI, and this is one that's actually kind of sort of been around for a bit, but here's an example of where, like, let's say like you're shopping for a piece of clothes, right? And you could upload a photograph of yourself, right? And you can choose a garment and take that garment and put it on your body to see what it would look like, to see if that's the right color for you or if that's a good style for you. That's kind of cool too, right? And they use the generator discriminator approach, you know, to do this, by the way. All right, let's take a look at some of these variational encoders here. I'm going to run this video here as well. This does not take a very long time.
When Brad Schimmel was Wisconsin's Attorney General, thousands of rape kits went untested.
Dear fellow scholars, this is 2-minute papers with Károly Zsolnai Fehér. As we have seen in earlier episodes of the series, neural networks are remarkably efficient tools to solve a number of really difficult problems. The first applications of neural networks usually revolved around classification problems. Classification means that we have an image as an input, and the output is, let's say, a simple decision whether it depicts a cat or a dog. The input will have as many nodes as there are pixels in the input image, and the output will have 2 units, and we'll look at the one of these two that fires the most to decide whether it thinks it is a dog or a cat. Between these two, there are hidden layers where the neural network is asked to build an inner representation of the problem that is efficient at recognizing these animals. So, what is an autoencoder? An autoencoder is an interesting variant with 2 important changes. First, the number of neurons is the same in the input and the output. Therefore, we can expect that the output is an image that is not only the same size as the input, but actually is the same image. Now, this normally wouldn't make any sense. Why would we want to invent a neural network to do the job of a copying machine? So here goes the second part. We have a bottleneck in one of these layers. This means that the number of neurons in that layer is much less than we would normally see, therefore it has to find a way to represent this kind of data the best it can with a much smaller number of neurons. If you have a smaller budget, you have to let go of all the fluff and concentrate on the bare essentials, therefore we can't expect the image to be the same, but they are hopefully quite close. These autoencoders are capable of creating sparse representations of the input data and can therefore be used for image compression. I consciously avoid saying they are useful for image compression. Autoencoders offer no tangible advantage over classical image compression algorithms like JPEG. However, as a crumb of comfort, many different variants exist that are useful for different tasks other than compression. There are denoising autoencoders that, after learning these sparse representations, can be presented with noisy images. As they more or less know how this kind of data should look like, they can help in denoising these images. That's pretty cool for starters. What is even better is a variant that is called the Variational Auto Encoder that not only learns these sparse representations, but can also draw new images as well. We can, for instance, ask it to create new handwritten digits, and we can actually expect the results to make sense. There is an excellent blog post from François Chollet, the creator of the amazing Keras library for building and training neural networks. Make sure to have a look. With these examples, we were really only scratching the surface, and I expect quite a few exciting autoencoder applications to pop up in the near future as well. I cannot wait to get my paws on those papers. Hopefully, you fellow scholars are also excited. If you are interested in programming, especially in Python, make sure to check out the channel of CentDex for tons of machine learning programming videos and more. Thanks for watching and for your generous support.
All right, so that's a nice little overview of how that works. But let's read through this slide here. This is kind of interesting slide. So let's assume the VAE is a magician with a box that transforms items. He wants to create new items like flowers. Takes multiple photos of the flower from various angles and distances to create a big data set. He recalls essential flower properties to construct a limited collection of variables that encodes data into low-dimensional latent space. Then it utilizes the compressed variables to create new flowers, right? He may include some randomness and unpredictability to make the generating process more distinctive. So this is kind of the process of how that works. All right. So the idea is to train a neural network to map data from the input space to the latent space, and then to use a decoder map to map the data back to the input space. However, unlike a standard autoencoder, the encoder of a VAE maps the input data to a probability distribution over the latent space rather than a single point. So in other words, it creates variable output is the way that I read that, right? So like it doesn't, you know, just because like it's mapping the way you write the number 9, it's not always going to write it exactly the same because you don't always write it exactly the same. There's some variability in it, but generally it's the right approach, right? So that's how it does that. There's a lot of different applications for this, and we've been kind of talking about some of them. And so including image and audio or image and video generation, data compression, and anomaly detection. They're very effective at creating high quality images that are sometimes you can't tell that they're fake, right? The technology is very impressive. And it can create images that are fake that basically can really deceive you as to how fake they are. All right. Another model for deep learning is this RBM, or the restricted Boltzmann machines. They're 2 layers of neural networks. They use unsupervised learning algorithms, so you don't have to have structured data going in. And the layers consist of one visible and then one hidden layer, as opposed to like the other networks, which have the in-between layer. Let's check out this little video here that should help to explain part of it.
So, what was it that allowed researchers to overcome the vanishing gradient problem? The answer to this question has 2 parts, the first of which involves a restricted Boltzmann machine. This is a method that can automatically find patterns in our data by reconstructing the input. Sounds complicated, but bear with me. We'll take a closer look. Jeff Hinton at the University of Toronto was one of the first researchers to devise a breakthrough idea for training deep nets. His approach led to the creation of the restricted Boltzmann machine, also known as the RBM. Because of his pioneering work, he's often referred to as one of the fathers of deep learning. An RBM is a shallow 2-layer net. The first layer is known as the visible layer, and the second is called the hidden layer. Each node in the visible layer is connected to every node in the hidden layer. An RBM is considered restricted because no 2 nodes in the same layer share a connection. An RBM is the mathematical equivalent of a 2-way translator. In the forward pass, an RBM takes the inputs and translates them into a set of numbers that encode the inputs. In the backward pass, it takes this set of numbers and translates them back to form the reconstructed inputs. A well-trained net will be able to perform the backwards translation with a high degree of accuracy. In both steps, the weights and biases have a very important role. They allow the RBM to decipher the interrelationships among the input features, and they also help the RBM decide which input features are the most important when detecting patterns. Through several forward and backward passes, an RBM is trained to reconstruct the input data. 3 steps are repeated over and over through the training process. With a forward pass, every input is combined with an individual weight and one overall bias, and the result is passed to the hidden layer, which may or may not activate. Here's how it flows for the whole net. Next, in a backward pass, each activation is combined with an individual weight and an overall bias, and the result is passed to the visible layer for reconstruction. Here's how it flows back. At the visible layer, the reconstruction is compared against the original input to determine the quality of the result. RBMs use a measure called KL divergence for step C. Steps A through C are repeated with varying weights and biases until the input and the reconstruction are as close as possible. Have you ever had to train an RBM in one of your own machine learning projects? Please comment and tell me about your experiences. An interesting aspect of an RBM is that the data does not need to be labeled. This turns out to be very important for real-world datasets like photos, videos, voices, and sensor data, all of which tend to be unlabeled. Rather than having people manually label the data and introduce errors, an RBM automatically sorts through the data, and by properly adjusting the weights and biases, an RBM is able to extract the important features and reconstruct the input. An important note is that an RBM is actually making decisions about which input features are important and how they should be combined to form patterns. In other words, an RBM is part of a family of feature extractor neural nets, which are all designed to recognize inherent patterns in data. These nets are also called autoencoders because, in a way, they have to encode their own structure. So we saw that an RBM can extract features, but how does that help with the vanishing gradient? We'll get to the second part of our answer in the next video when we take a look at the deep belief net.
So kind of a quick little explanation of how that model works. But here's some of the things that you should kind of get from that. Feature extraction and pattern recognition, recommendation systems, and then intra-pulse detecting and radar systems are some good examples. So let's start to look at some of the practical usages here. And we were talking about this early on, but take a look at this list. This is kind of an interesting list here. And some of these things, and I want you to think about this, are things that we're already using, right? So for example, fraud detection and self-driving cars and the virtual assistants that we have on our phones and our computers, or when we use investment modeling, of course, the facial recognition and some of these other ones. And so they're going to kind of like talk about a few of these here. So let's just kind of go through them. Here's a tool called 2Sense AI that is basically a company that focuses on biometrics. And I want you to look at this acronym here. So like you guys might not know what this one means. Does anybody know what SAS is? SAS? SaaS? Everyone knows what that stands for. You can Google it, of course. But it's a software as a service, right? So in other words, people don't buy the software and install it on their computer. They buy it as a service online, and then you attach to it online. But it's basically designed for doing authentication. So for example, when I log into my credit union account on my app on my phone, I let the app read my fingerprint to verify that it's me, as opposed to typing a username and password. Why? Because when I'm on my phone, I might be holding stuff, or it might be somewhere I want to check my account balance, and fingerprint on my fingerprint sensor on the back of my phone is a lot easier to work. And so this is what this company does, right? So like people can spoof your username and password because they can just steal it from you. They can't really steal your finger. Well, I'm sure you've seen movies where people just cut off somebody's hand when they got the fingerprint, right? But in principle, right, they can't do it. Here's another one, autonomous self-driving cars, and they use Teslas as an example. I am gonna spin this video here. Let's check this out. This is pretty neat.
Today you and tomorrow you aren't the same person. If you're tired of what Today You is doing, get an accounting fundamentals certificate from WGU School of Business and get a whole new Tomorrow You in just 6 months. Enroll today at WGU.
Hello guys, it's Smita and welcome back to another video. Today I'm going to be talking about how Tesla uses deep learning in its self-driving cars. In the past couple of weeks, Tesla has released a new software update which has a cool new feature called Smart Summon, which allows you to summon your car towards you. Experts have even said that kids born today will never need to learn how to drive, simply because all cars in the future will have self-driving capabilities. When Elon Musk first created Tesla, he claimed that their goal was to create a car which drives just as well as humans. Now that goal has transformed into creating fully autonomous cars. Self-driving cars will not only save time, money, and resources, but they actually save lives as well. Let's take a deep dive into how the Tesla autopilot works and how the automotive industry is moving towards an autonomous future. Before we get into how Tesla uses deep learning, let's actually find out what deep learning is. Deep learning is a specific subfield of machine learning. In the current state of the internet today, there is a large amount of data floating around from all different sources. However, this data is largely unstructured and it's quite useless in that form. With deep learning, we're able to dig through large volumes of data and automatically identify patterns and extract properties and features from complex, unsupervised data without the involvement of humans. This data can come in many forms such as images, text, handwriting, and even sound. In fact, the deep learning models that we have today are more accurate than humans at detecting handwriting and even images. To understand how the technology behind Tesla's self-driving cars work, we have to understand how Tesla makes the car behave like a driver. The two main skills that a car should have is vision and decision making. When we talk about vision, we're talking about the car's ability to precisely identify what it's looking at. Tesla's cars should have the ability to identify numerous things such as cars, stop signs, pedestrians, roads, buses, traffic lights, intersections, and even vegetation, and where the road meets the footpath, and so on and so forth. So here's a really simplified example of how Tesla uses deep learning to train models to identify cars. It starts off by feeding tons of different images of cars to the model. The model then uses deep learning to understand how to identify cars. So basically, it learns the different features that cars have, which is unique to them, such as having 4 wheels, having doors, and so on and so forth. Once the model is sufficiently trained, you can introduce a brand new image of a car that the model has never seen before, and the model will be able to identify that it is in fact a car. And this process is repeated for everything else a car should be able to identify, such as stop signs, pedestrians, and so on. Now, the biggest issue for Tesla cars is to carry out these computer vision tasks in real time. This takes an extremely huge amount of computing power. This year, Tesla actually unveiled its own chip that it works on, which is used inside of its self-driving cars. It claimed that the chips are 21 times more efficient than NVIDIA chips which they used earlier on. One really cool thing is that each Tesla computer actually has 2 AI chips to increase redundancy. In the case that anything were to fail, there's always a backup. Even more interesting than that is the fact that each of the chip actually makes its own decision of what the car should do next. The computer then compares both of these decisions. If the chips actually agree, the car takes the action. If the chips disagree, the car just throws away that frame of video data and tries again. The chips are optimized for self-driving cars and performs 36 trillion operations per second, which is a ridiculous amount. There is still some work to be done in terms of getting faster computing powers and more efficient algorithms before we arrive at fully autonomous cars, but most of us will probably see it in our lifetimes, and that is something to be truly excited about. Hope you guys found this video.
All right. And I think I've shared this story with you guys, but I have ridden in one of those cars. It is absolutely blow away. Technology is basically there. And I think that's going to be a reality in the future that many of us won't have to drive anymore. Now, there is the caveat, right? We have to be able to afford to buy that car that drives itself, right? And the more we go into the future, I think that technology will just get better and better. Here's another example of a company that does monitoring of investments, right? So they check all the data feeds from the stock markets, and then, look for opportunities basically. And I'm going to start accelerating our flow here a little bit. There's also these recommendation systems. So like, for example, like if you watch certain videos on YouTube or you look at certain products on Amazon, that those start to learn your behavior and start to recommend things based upon what you've done before or what you've looked at before, which makes a lot of sense. I'm not sure how long this video is.
The very first recommendation engine that we built using collaborative filtering was considered revolutionary 20 years ago. It was an early version of a machine learning algorithm. That recommendation engine helps customers discover related items, like a camera bag or the lens for a camera that a customer had just purchased. It's still on the site, and it's still a huge help for customers. When we later combined collaborative filtering with heuristics to make recommendations, we were able to give customers personalized recommendations rather than just showing them popular items. Fast forward a few years. Add in the exponential growth of computing power provided by Amazon Web Services, plus the improvement of sophisticated machine learning algorithms. And we start to get dramatically better results, on the order of 2 times better than a typical algorithmic improvement. That's a once-in-a-decade leap. That helps us to personalize our content and recommend goods that a customer would like to buy and movies that a customer is more likely to watch. Let me explain how we achieved these goals. And it wasn't a straight line to realize the improvements. In 2012, we wanted to update our product recommendation algorithm to improve personalization for customers. We started from state-of-the-art graph clustering techniques. Then we shifted our approach under the hypothesis that deep learning methods would outperform matrix completion methods because we could take advantage of nonlinearities. But we found this approach performed worse than not only our best collaborative filtering algorithm, but just a simple bestseller, a ranked list. Then we used a common artificial neural network called the sparse autoencoder. But it was still not as effective as collaborative filtering or the bestseller list. In fact, we tried methods based on singular value decomposition, bilinear regression, and restricted Boltzmann machines. Nope. None of these matrix completion-based methods underperformed or overperformed compared to our production algorithms and simple lists. We were surprised that the state-of-the-art methods would perform worse than a simple bestseller list. So it prompted us to take a step back and think about the objective function that we were trying to solve. We looked inside the black box to identify what was happening. I'm going to explain this in the context of Prime Video, but the same approach applies to many products on Amazon. We found that matrix completion methods learned that classic or Oscar-winning movies would be of interest to many customers. Makes sense. However, we saw that given an evening at home on a rainy Saturday, customers prefer to watch a newly released movie rather than an old movie. In other words, Captain Marvel beats Casablanca. This learning became the foundation of our winning approach. We developed a new model for recommendations using multi-layer neural networks for classification. We trained the model using a loss function for predicting what customers wanted to watch in the next week. What you see on the screen is the formulation behind the model. We took historical movies that customers were watching in order to predict the movie a customer wanted to watch next week. The neural network classifier outperformed other neural network-based approaches that are much more complicated. The simplicity of this model made it inherently more scalable, so we could expand to many millions of products and hundreds of categories across Amazon. And it performed 2 times better than collaborative filtering, so we had a winner.
All right.
The very
pretty deep stuff, and it shows that these companies are employing these things on their live websites, and they're driving it with all these technologies, and they do experiment and they figure out, what works better, and it's not accidental, right? They have some really high-level people working on these. Here's, some. We're kind of getting towards the tail end here, if you guys are wondering. So we're doing pretty good on time. We should be able to finish up. But what's kind of neat about some of this stuff is when we start to actually generate stuff that's synthetic data, as they're saying here, that is so stark and impressively like real looking. Why do we do that? So this goes back to Kathleen's question, right? And the reason we do that is because it costs money to actually gather the real images. So if you're going to like train a model on people's faces, well, you got to like ask every person for permission. That's kind of an interesting thought, right? And how many of us don't want to even be part of it, right? A lot of us, even if we're tech people, we don't really want to be part of it. Now, of course, if you're posting stuff on social media, I want you guys to think about this. You're putting it out there, so it's grabbing it. And you're giving like Google and Facebook and whoever permission to grab those images. And then, so think about that when you're posting stuff. That's, why did they create a deep fake of Tom Cruise? Because his face is all over the internet, right? Because he wants to promote his movies and his whatever, so that's kind of the why. I think this is kind of interesting. All the stuff that you see on the screen here are synthetic images generated by a GAN. Kathleen, you have another question.
Yep, just a real quick question. With the fake images that they're creating, is that ethically violating anything with identity, your identity theft? You haven't signed off on using your likeness? Any concerns there with that concept?
Well, if they're taking your likeness, like let's say the large picture of this guy here on the left, right? He's not a real person, but clearly his features are based on other people's real features. So they could be taking the nose from one person and the hairline from a different person and whatever, like all the little details, and stitching them all together to create a new image. And it is very convincingly looks like a real image. You have to admit, right? Yeah, there are ethical concerns, sure, right? And this is a discussion I had with somebody I used to work with. In fact, when I was teaching at the Art Institute in Milwaukee, and our dean at that school was a very prolific graphic artist, and she had the contention that whenever she would post any of her images online, that other people would sample those images, and then it's gotten to the point where AI is recreating some of the stuff that she created, but creating its own version. And she has an ethical, she thinks it's stealing. So if that's not a real person that we're looking at there, we're stealing the features from other real people to make it look convincingly real, right? So is that ethically wrong? I don't know. But why do they do it? Because it's cheaper to generate that face to train a different model for something else than it is to ask somebody for permission to use their actual face. But once again, if you're posting your stuff on, you put a picture of yourself on Facebook, you're not keeping it from anybody. It's out there. People are grabbing it. It's a very interesting thought, right? It's not quite intellectual property. It's like you're putting your identity out there. I think what's kind of interesting is some of what's going on here, which is how they take stuff that is kind of like not really high resolution, like you might have a really horrible image, and they're using the AI to kind of fill in the gaps. This is kind of interesting. So if you look at like this first image here, like this is maybe like an old digital photograph, and then they put it into these deep learning models that basically allow this low res scan here or whatever it was to increase its resolution and make it look really, really good. Like they took it with a really great camera and it was a great photographer, but it was really not. So this is the other aspect of this, is taking low res stuff and making it look high res, right? And when you look at, like, for example, old, videos or movies or TV shows or whatever that were like shot in the old days that weren't high def, and now they're re-releasing the stuff because they put it through this process. And and the thing about this, like when they took old black and white movies and colorized them, you guys ever watch any of those? And it's like, oh wow, did you see the colorized version of whatever? And the early versions of it weren't all that great, but now they have technology that's doing it that does an amazing job and makes it look crisper and better than it ever did in the first place. Another thing that they're doing, and this is a thing that I'm seeing in some of the Adobe products too, is where they take an image that's missing pieces of the information and they're generating the stuff that's missing and making it look very convincing. This is a tool that is available in Photoshop where like you can take somebody out of a picture, like, hey, look at all those weirdos in the back of our wedding picture. You can delete them and then regenerate the background. And it's very convincingly real. I want you to notice that some of this stuff, so the tool that they're using on this one to take the blank spots of the photograph and fill in the image is an open source framework. And oh my God, if it's open source, that means you don't have to pay anything for it. This is just out there for the taking. Now you can imagine that the generative AI engines that have access to these tools, if they're open source, they're using code bases that are available for free. And often, and I think that's what that one guy was showing in that Manus video that I was kind of showing earlier before class, that it's utilizing other AI engines as part of its process to do its work, but it's doing so autonomously. It's not asking you for permission to use somebody else's open source AI library to generate the work it needs to do. It's just doing it intelligently on its own. It is kind of scary stuff. But how does the technology work? Well, it looks at patterns. I mean, like, for example, you assume these are leaves. You assume this is going to be rocks. You assume that's going to be part waterfall, part cliff, and it's painting that in. How is it doing it? It's looking at the stuff around it and kind of guessing as to what should be it. But if that's an open source library, that's kind of a wow. It really is. All right. So that's going to wrap up the content for this evening, folks. And no, I'm not giving you a quiz, so don't freak out. So I'm going to stop the recording here. This video is now officially over. And I see what's happening now. I thought I paused the video before. It's not letting me stop the video. My Zoom is failing me here. So I'm going to have to use a keystroke command